that one.
I found the homework. It did come back. It's just I forgot to say it on Friday because we were.
A biconditional statement. Biconditional statement. This is the last definition of the stuff from 2.2 that we haven't had a chance to talk about yet. We kind of, really wasn't that big of a deal, but most things in geometry, most definitions and stuff, can be written in terms of what's called a biconditional statement. A biconditional statement is just a regular statement that's true going forward and backwards. Yes, ma'am? Yeah, this is just that last little blurb in 2.2. To be honest with you, it's not a really big deal what section this is out of. We only use it, we use it in definitions more than anything. So it's just kind of like a little FYI type thing. So this biconditional statement basically says is that is a statement that is true going either way. And I hate book definitions. I think book definitions are they're long-winded. They're sometimes really difficult to distinguish what's going on within them. So a lot of times when I come up with definitions to help you guys out, I like to kind of just use an example and go from there. So what I would say about this biconditional statement, the easiest one that I can think of is this. If an angle measures 90 degrees, then it is a right angle. Do you guys agree? That would be what I would call my generic conditional statement. P implies Q. P to Q. All right. If I say the converse of that, it just goes the other direction, Q to P. If an angle is a right angle, then it measures 90. So this is our P to Q. And then if I flip it, if an angle is a right angle, then it measures 90 degrees. Is that true? The answer is yes, it's true. All right. See how it's the same going both directions? When it's the same going in both directions, you can rewrite it as what's called a biconditional statement. We use the term if and only if. An angle measures 90 degrees. Now, if and only if is a lot of letters. It's a lot of words to write out. So, just like most things in geometry, we abbreviate. If IFF stands for if and only if.
Wait,
That's
what?
not confusing because there's no O.
That's just how they write it. They've been writing it like it's in textbooks. There's textbooks in college textbooks that use that. IFF. If and only if. If.
I don't like it.
I'm sorry. An angle measures 90 degrees if and only if it is a right angle. Done. That's a biconditional statement. That's what they're going to look like. If it is true going in both directions, you can put an if in the middle of it and call it a day. You see this terminology of this if and only if all the time with definitions. A triangle is a scalene triangle if and only if all the sides are different lengths. Two lines are perpendicular if and only if their opposite slope or their slopes are opposite reciprocals. Things like that. You've probably heard the terminology if and only if before, but that's what that means. It means that it's the generic statement and its converse, saying it backwards, means the same thing. That they're both true. That's all. Okay. Most people are like, whatever. You'll see these if and only ifs a ton as we get into more and more of the geometry parts. We have a ton more definitions and things like that coming through later on. Think about a midpoint. X is a midpoint if and only if the segments that divide are equal to each other. Things like that. Okay? If.
Are you still writing?
Don't harass her, maybe she just wrote slowly to stuff.
I'm not harassing her.
Harassing
Because
you.
I was copying what she wrote at the top because he scrolled down.
Woe is you. I'm joking. Law of syllogism. This is I got two new definitions out of this, and we'll do a couple examples. All right. Law of syllogism. This sounds and looks really, really weird for something you already know. Again, law of syllogism is also known as, what do we call it? I just forgot what it's called. Transitive property. You've seen that before, you just probably forgot what it was. So again, the easiest thing to do is to start these things with an example.
Ew.
Bless you.
Tom, Mary, Joe.
Easiest thing in the world to talk about this law of syllogism
No.
is to use an example. Tom is taller than Mary. Mary is taller than Joe. Therefore, Tom is taller than done.
What?
That's all it is.
Oh.
That's all it is.
This?
That's the law
Oh,
of
I thought it was
syllogism.
more complicated.
No,
I thought
no,
it was
it's
an
not.
Equation.
Tom is taller than Mary, Mary is taller than Joe, therefore Tom is taller than Joe. Done. Same idea as this. If A equals B and B equals C, what can you say? Done. That's the law of syllogism. One thing I want you to see here, though, is that notice that these parts are repeated. It's the ending statement of the first line. It's the starting statement of the second line. If you read it, you'll see that they're diagonal across from one another. A lot of times within words, you will see it like that. That's what shows the law of syllogism. Basically, if they're diagonal from one another, they kind of cancel each other out, like they're slashing them apart, and then those other two just equal each other out. That's transitive property, law of syllogism. You've seen this a ton of times, you just never realized it, right? If the power goes out, the refrigerator will stop running. If the refrigerator stops running, the food will spoil.
Yeah, that's okay.
We show you. If the power is off, don't write this down, this is too many words.
Okay.
If the power is off, then the fridge doesn't run. If the fridge doesn't run, the food will spoil. You don't have to chase it. Again, notice, it's the ending of the first statement, it's the start of the second statement, which means the power's off, the food will spoil. That's all that means. Tom's taller than Mary, Mary's taller than Joe, Tom is taller than Joe. Done. Mhm. What? We don't have to chase the refrigerator, correct. That's pretty much it. Now you're probably all waiting for the hard part of this. Yes, and the last time I checked, most refrigerators are slow. You could probably outrun some of them if they're chasing you. I'd watch out for the little toaster though. The little toaster is really, he's nasty. You the cartoon, the little toaster?
Yeah. He always brings his blanket.
Detachment. Here's the other one. Law of detachment. You're going to hear a very obvious difference between syllogism and detachment. Syllogism flows. Tom's taller than Mary, Mary's taller than Joe, Tom's taller than Joe. Flows right through it. Detachment is choppy. Detachment is very choppy. Let me write something out here. If it's Sunday, I'll go to the farmer's market. If it's Sunday, then I'll go to the farmer's market. Today is Sunday. That's all it is. That's all it is. Notice what it's doing. The first statement is you got your hypothesis, conclusion, you know, that P and Q. If it's Sunday, then you go to the farmer's market. The second statement says, it's Sunday. So then it tells you, okay, what do you have to do then? Go to the farmer's market. Detachment is so much choppier in the way that it sounds versus that syllogism, that real easy flow to it. This one, basically, in technical terms, it's saying that the first part of your statement is true, which means the second part of your statement has to be exactly. That's it. All right. You use this with, you see this a lot with logic and reasoning. Okay, you see this a lot. It's kind of like what we did on Friday. So-and-so did this, so-and-so did that. Well, he did this, which means somebody else had to do something else. It was just kind of those ways that these things write themselves through. Let me give you another one. If an angle measures greater than 90, then it's not acute. What can you say? What's that? What's not? Which angle? If an angle measures greater than 90, then it's not acute. Angle A is 112. What can you say? What's not acute? Angle A. So this was your going part, the start of it. So you can come up and say then, angle A is not acute. Done. That's what detachment does. It's a choppy way of writing logic. Okay? That's it. That's really all it is. What's that?
Like for the syllogism, it's like a three-way statement.
Kinda. I see where you're going with that.
There's three parts to it.
There's three parts to this one too. It's just,
Well, like I get that, but like the subject.
well, what can happen, I'm just going to show you an example. What can happen with the syllogism though, is that you could have, where is it? You can have this. Sorry about the line in the middle. If I give you those two statements, what would you say for your third statement? If you wear school colors, then you have school spirit. If you have school spirit, then the team feels great.
Team feels great, the team wins. No.
Careful. Again, and this is the idea where you started with two statements. How do you come up with a third? In this case, is something repeated.
Oh, yeah, those two across from each
They're,
other.
these two are repeated diagonal from one another.
If you wear school colors, the team feels good.
Exactly.
So if you see something repeated twice, you can cancel those out.
If they're diagonal from one another. If you
It's like-
end with one and it starts with the second.
So it's like division, like if you like.
Yeah, if you want to think of it that way. And then, like you said, then this part drops to this part.
Okay.
Okay? And that's what it does. That's what it does. That's what the law of syllogism says. Because you have that diagonal repeater.
How do
Okay?
you do the attachment?
Well, just like this. If an angle measures 90 degrees, then it's not a cube. Angle A equals 112. Therefore, angle A is not a cube. It's choppier. You're saying that the first part is true. Let me show you another example. If you eat too much turkey, then you will get sick. Kinsley got sick. Ate too much turkey. That's it. That's detachment.
Oh.
See how it's choppy?
Okay.
There isn't an extra piece to it. And if it was syllogism, I could have done this. If you ate too much turkey, then you will get sick. If you get sick, then you puke. What would be your third statement out of that?
If you eat too much turkey, you will puke.
Exactly. It's a very crude example, but you see how it. If you eat too much turkey, then you get sick. If you get sick, then you puke. Therefore, if you eat too much puke, then you spit turkey. If you eat too much turkey, then you puke. That's all it is. It's a horrible example, but you get but you see how it flows.
Yeah.
Whereas the other ones, we were just looking at them. It's
It's here, it's here, it's here.
yeah, it's very very choppy.
Okay.
You know. Now, just reading this one has all three parts to it. See how it flows very smoothly? If 2 is acute, then 3 is obtuse. If 3 is obtuse, 4 is acute. If 2 is acute, 4 is acute. It just flows itself through. Okay? That's what we're looking at. Now, the other thing I want to talk about today is how you can infer information from a diagram. But you have to have your Chromebooks. I didn't run this off. There's no reason for you to draw this picture. So, open your Chromebooks out, go to the website, and I'm going to show you guys what I'm looking for. If you don't have your Chromebook on, you just sit next to someone that has it, please. And I'll show you what I want to look at. What chapter are we in, ladies and gentlemen? 2. So I'm going to say we should probably go to Geometry Chapter 2. That's fine. You won't find the information that you're looking for. Okay? And what I want you to do is scroll down to where it says 2.4 Practice B PDF, and just click on it. 2.4 Practice B PDF, and then click on that, please. All right. It's so fun to watch people play on their phones when they're on their computers. It's great. Come on, put it away. What? All right. So now scroll to the second page of the PDF file, please. And I'm going to look at this diagram right here. And I want to walk you guys through how you infer information from a diagram. Because as we go further into geometry, more and more we're going to be given specific diagrams to start with. Also, we're going to have to be able to draw and come up with our own diagrams as we get into this as well. Now, this is, well, I didn't want you to draw this because this is awful. But hey, we've got a screen, we can look at it and call it a day. So as you go through bits of information that's given to you, we want to be able to tell if it's true or false. Is it something you can infer from a diagram? Well, in this first one here, it says points A, B, D, and J. A, B, D, and J. Are those points coplanar? What does coplanar mean again?
On the same plane.
On the same plane, yeah. Are those guys on the same plane?
Yes.
Yeah. Those are on the same plane. Now, we can say that those guys are coplanar because they're on the same plane. All right? Can we say that angle EBA, EBA, we say that that's a right angle? Why?
No.
We don't know that. But why can't you say this isn't right?
It's in the box.
Exactly. Remember, right angles in diagrams are going to have that little box in it.
Oh.
Remember that little square part? That's what's going to show that it is. Now, if you see that in a diagram, obviously that means if this was there, that has to be a right angle. But since it wasn't, you can't assume it. You don't want to make an angle side-side out of you and me. Now, sometimes you will have information that'll say angle ABC or whatever is a right angle, but the diagram might not show it yet. So if you see that, then you would put that little box into the diagram if it's given, that information is given to you. But in this case, we don't know anything for it. So we go to the next one. Are points E, G, and A collinear? Remember, collinear means they're on the same line. Are those points on the same line? Oh, I forgot to tell you, we've got calculators in if you guys still need to buy a calculator. Finally got them. Are they on the same line? E, G, and A. Nope. Is line FG perpendicular to the plane H? Plane H is the plane that's shaded gray. Is that line FG perpendicular to it?
We don't know.
It intersects it, but is it perpendicular? Because if it was perpendicular, what would we see? We see the right angles. Very good. Do you see right angles there? We don't have any markings of it, so we can't assume it. Now, what about angles ADD and EBC? Are they vertical to one another when you look at it? Remember, vertical angles, their opposite rays form form lines. Can we say that are these two angles here and here? Well, are they even the same plane? Are they in the same plane and are they vertical?
Aren't they vertical because they cross with the angles?
The angles do, yeah. And if you look, see this line DE and AC, they're on the same plane. They're on that plane K. What this diagram is, and I had a piece of paper with it. If you can think of what this looks like, it's this. It's just two sheets of paper that intersect with each other. That's all it is. It's just two sheets of paper that intersected. All right. And yeah, those guys would be vertical. Vertical angles is one of the things, or vertical angles are one of the things that you're going to be able to find in diagrams to utilize a lot. Because we know that vertical angles are what? More specifically, they congruent, yes, they're congruent. Vertical angles are congruent. That's one of the things that we're going to use a ton of when we get to triangle groups. Okay. Do planes H and K intersect at line AB? You guys are all looking at it. Do they intersect there? Yeah. Do lines F, G, and DE intersect? at your screen. You have it right there. You guys are, I don't know why you're looking up here. You've got it one closer. Does this
Yeah,
line
they do.
intersect this line? Ah, look carefully.
Oh, no.
What does that little dotted line mean again? It's behind it. These guys don't intersect, but yet they're not parallel. Remember what that's called? The two lines that don't intersect, that are not in the same plane? No, these are lines.
Non-adjacent?
No, these are lines, guys. They have ends of angles. It starts with an S and ends in a Q. Skew. Remember we talked about skew lines? Chapter 1. Boy, oh boy. It's gonna be a long first semester if we don't remember simple definitions, guys. You gotta remember your definitions. We talked about them. Ceiling track versus the floor, or going the other direction. Those lines will never intersect each other. Don't say it's a fall. The roof falls in. No, you're thinking it. Shut up. Doesn't mean you have to say a word and I know she's sugar face. Those two won't intersect each other because they're skewed. They're in different planes. And then lastly, can you say anything that is there any way of showing that GCA and angles CBD are congruent to one another? Look at your picture. Look at your picture. Does it say that anything on there that shows that those two are congruent to one another?
No.
What would it have to have?
Fine.
Yeah, the little tick mark things. Yep. It'd have to have those tick marks in it. Since it doesn't have it, you can't assume it. There's a lot of things that you guys are going to tend to try to do with diagrams and stuff. You're going to make stuff up. You can't make stuff up. You can only deal with what is actually really physically there. Otherwise, it's not going to work. Each and every year, people try to make things up. Don't even start trying to make stuff up. Okay? When you have, and it's a little tip for later on, when we start talking about proofs, if you're working with angles, then you're not working, if the proof is about an angle, then you don't use any definitions that deal with segments. Because last time I checked, segments and angles were different. Same thing goes for if you're working with segments, you're not dealing with angles, okay? You'd be surprised at how often you guys will do that. The other thing is, speaking of the drawing diagrams, is to look at this bottom part of the page. Create a map. And this is one of the things that you will do with geometry a lot, is that they're going to give you a bunch of definitions, a bunch of scenarios within a picture, within a diagram, that you're going to have to draw up on your own. So if I look at this one, when you draw a map, what do you have to have? Yeah, a legend, a key, something. Maps usually have a compass. Do you remember what a compass does? What goes up here on a compass? North. Then what? Which is it? Never eat soggy waffles. Yes, ma'am. There you go. Do that too. Now, one couple of the definitions that you're going to hear on these things is the term due south, due east, due west. What does due south mean? What's that? Go south. Okay. So if building B is due south of A, if I put A on the board, where do I put B? All right, so if I put A here, where do I put B? Which is what direction according to A? Below it, right? Like Chicago is due east of here. If we take a right and just go that way 67 miles, we'll be in Chicago. All right? That's the idea. What does it mean if I say northeast? What direction do you go? Just point with your arm, according to ours. Yeah. That way is northeast, southeast, southwest. Do you know what east, northeast would be? Now, if I say northeast, that's usually splitting it in the middle. If it says east-northeast, you know what that means then? It's more east. It just means it's more east. That's all it is, in case you ever hear that. Okay. Now, obviously in this class, we're not going to worry about bearings or anything like that, but there are, you know what I mean by the term bearings? If I say an airplane is going at 75 degrees northeast, that means it's just going this way off north 75 degrees. We deal with bearings and things like that a lot in pre-calc. So it's a lot of trigonometry stuff that you can do. Nautical is different than aeronautical. Aeronautical? Yeah. Airplanes. Airplanes and boats are different, in case you didn't know that. Unless it's an airboat or a boat plane. All right, anyway. So A and B, or B is due south of A. So we placed it, due south. It's on street 1. There's a 1. C is due east of B. Where do I put C then? To the left or to the right of B? Correct. Then it says C and B are on street 2. D is southeast of B. Where does that go? Writing down, diagonal here. Okay, and then it's on street 3. Building E is due west of C. Now, if I put E west of C, that means it could be either here or here. It could be on either side of B because it's still west of it. Do you agree? But the next, so we don't know what to do yet, but the next clue tells you what to do. The angle DBE formed by streets 2 and 3 is a cube. According to our diagram, which of these two angles is a cube? This side, the right, or the left?
The right.
Correct. So that means E has to be between. Using logic and reasoning, you can come up with stuff like that. That's kind of what you did on Friday. You use logic and reasoning to figure out, okay, Tom is married to Sue because Sue, his last name is Smith, and Tom's whatever brother is Bob. And they had a red van in camping spot 41. I'm just making that up. But this is the kind of thing that we start to do more and more of. We're going to start building and creating diagrams from given information. Okay? It's really not difficult, just as you go through it. There were questions here. Yeah. Do you know why everything is drawn up in grids like that for streets? Why are streets perpendicular and parallel to one another? That's exactly right. It's the easiest way to get around. If you look at most towns, whether it's DeKalb or Chicago, New York, things like that, most of their streets in the original downtown areas and stuff, they're all parallel and perpendicular to one another. Even in DeKalb, if you go down by the tracks and stuff, that most of those streets over there are all parallel and perpendicular to one another. As you get out to some of the other spaces and whatnot, you see it like in the subdivisions, you don't get that as much. But when you're in most town center areas, everything is usually parallel perpendicular. Even like little old Malta down the street, as you get in there back by the gas station, you get behind it where the old high school and all that stuff was. All those streets are just parallel and perpendicular to one another. Most towns are like that. My wife's grandparents live in this little town called Aerosmith, Illinois, just east of Bloomington. It maybe has 30 houses in it, and there's 5 streets, or there's 10 streets. Yeah, pretty much. They've been there forever. They used to have a little store on the corner there, so you know they lived there for 4 generations, 5 generations, something like that. Little farming town. I couldn't either. But these little towns, they're all parallel streets and perpendicular streets, just the way you can get through. If you ever get lost in New York, streets they only have streets and avenues, and they're all numbered. They go up and they go down. That's it. It's very easy to get yourself around town. The last little bit then works out to be what I want you to work on tonight. I'll give you a little bit of time because this works out well.
There's two sections. We have section 2.3 and section 2.4. One of them's on page 90, the other one's on page 100. And I'm going to walk you through the first one to make sure we got them right. 4 through 9, and then 14, 23.
While you have the Chromebooks open, go flip over to the book tab, and scroll to page 90. So I want to show you what happens as we start to work through these. Put this up for a second so you can finish writing that out. All right. So just for a quick example, if you look at these first couple of problems, it says make a valid conclusion of the situation using either the law of detachment or the law of syllogism. Okay? So the first one, if the measure of an angle is 90 degrees, if the measure of an angle is 90 degrees, then it is a right angle. The measure of angle A is 90. So what can you say? What is? Angle A is a right angle. There's your answer. That's it. If you want to play the clarinet, then you would play a woodwind. If you play a woodwind, then you are a musician. Use the law of syllogism, what drops out? The woodwind part drops out, so your final statement would be done. That's all this stuff is, guys. It is very, very, very straightforward. Okay? Go ahead and start working on those things, and we'll call it a day on it. For what? Oh, we actually did that one in our notes. We did that exact one in the notes, too.